Hello and welcome to this episode of Math with Martinez. In today's video, we are looking at some really specific types of exponential growth and decay. We want to be able to analyze situations that are modeled by exponential functions so that we can solve real world problems. So let's go ahead and begin. I want to begin by just highlighting some key vocabulary related to exponential growth and exponential decay. And throughout this video, I'm going to use green for exponential growth and red for exponential decay. So exponential growth occurs when a quantity exponentially increases over time. Key word that I want you to be aware of, increases, is that key word for exponential growth. And conversely, exponential decay occurs when a quantity exponentially decreases. And again, that key word is decreases. If it's decreasing, then that's exponential decay. Now, what does the exponential growth function look like? The exponential growth function is typically a function f with respect to t, where t is time, where you take your initial amount and your base is 1 plus the rate of growth to the power t. Again, we see here, let me highlight it for you. A is the initial amount and R is the growth of is the rate of either growth or decay expressed as a decimal. And T is the length of time that we are dealing with. Exponential decay is much like it, except that it is a function with respect to time where we have our amount. And then it is 1 minus our rate to the power of t, where t once again is time. So let's take a look at a few examples here and see if we can decide what kind of model we're dealing with, growth or decay, and then answer the very specific questions. Brooke started her career with an annual salary of $32,000. Each year thereafter, her salary increased by 2.5%. Write and use an exponential growth function to find her salary when she retires after 30 years. All right, so are we dealing with exponential growth or decay here? Which one is it? Well, the word that should have stood out to you here is increases. Her salary increased, and therefore we're dealing with an exponential growth model. So we're going to use the function with respect to time. Now let's begin to substitute our specific amounts. A is the initial amount. What was the initial amount that Brooke started her career with? It was an annual salary of $32,000. And then we'll have 1 plus our rate, but our rate must be expressed as a decimal. So we need to take this percentage and rewrite that as 0.025. And that is raised to the power of t. So, ladies and gentlemen, that simplifies. Inside, we would have 1.025, and that is a number that would represent a base that is bigger than 1, therefore it is growth. Now, let's go ahead and find what her salary will be when she retires after 30 years. So that means our function with respect to a time of 30. So we'll take her initial salary, the rate at which her salary is increasing each year, and it's going to be raised to the power 30 because that represents time. And what is that going to be? Can you guys go ahead and take the expression there, this expression, and go ahead and substitute that into your calculator and see what does that simplify to? What is her salary? All right, well, you should have had that the salary would be $67,122.16. That would be her salary upon retiring. Pretty amazing how that exponential growth affects. All right, in number 2. In 1995, a magazine had 14,000 subscribers. The number of subscribers increased by 40% each year thereafter. Write and use an exponential growth function to find the number of subscribers in 2016. Ladies and gentlemen, is this going to be exponential growth or exponential decay? Well, based on this word increased, we know it is exponential growth. So we have a function with respect to time with an initial amount of 14,000. We're going to add our rate of 40% expressed as a decimal to 1. So this simplifies, and our rate would be 1.4, which is greater than 1. So that is representative of exponential growth. Now we want to know, what will our number of subscribers be in the year 2016? But that does not mean that we're going to type in 2016. No. To find the appropriate t, we need to see how much time has passed there. So we need to take 2016 and subtract 1995 from that to see how much time has actually passed. How many years is that? That is 21. So we are looking not to find this at an input of 2016. No. We're looking not after 2,000 years, but just after 21 years. So with that growth rate and a time of 21, what is going to be the number of subscribers? We should have 16,398,978 subscribers. That is pretty impressive. All right, let's take a look at example number 3. In example number 3, we are looking at Kate, and let me read it for you here. Kate drank an energy beverage with 150 milligrams of caffeine. Each hour, the amount of caffeine in her system decreased by about 12%. Write and use an exponential decay function to find the amount of caffeine in her system after 8 hours. Ladies and gentlemen, is this exponential growth or decay? This is now, we're transitioning to exponential decay because we see that this is decreasing. So this is going to be a function with respect to time where the initial amount of caffeine is 150 milligrams of caffeine. And we are then going to subtract the rate at which it is decreasing, which is 12%, expressed as a decimal would be 0.12 to the power of t. So this function with respect to time actually simplifies. When I take the difference there, that is going to be 0.88, which is a base between 0 and 1. So that would be exponential decay. Now we want to find the amount after 8 hours. So this function at time 8. Initial amount and our base, where our exponent is 8. how much caffeine is in her bloodstream after 8 hours have passed. Well, there would still be 53.95 milligrams in her bloodstream, which goes to show that Kate probably does not need to, well, it didn't say coffee, but I'm guessing it was coffee because that's about how much a typical cup of coffee has. She would not need to drink more coffee that day. That is still sufficient amount of caffeine in her bloodstream and therefore should not drink more, otherwise she's going to stay up all night. Now, number 4, the half-life of mercury is the half-life of mercury 197 is 3 days. What we want to do is write and use an exponential decay function to find the amount of mercury left from a 50-gram sample after 20 days. Ladies and gentlemen, is this exponential growth or is this decay? What are we looking at here? This is exponential decay because we are talking about, well, it says it straight away there, right? So what we have is a function with respect to time where the initial amount is a 50-gram sample. And what we have here is a half-life, and so that's telling you the rate. We're saying the half-life, or 50%, would be remaining. It decreases by 50%. And so we would write that as 0.5. So this function can be written as 0.5 t, just like so. So what we're looking at here is what is it going to be in 3 days? Now, my apologies. We need to take our time and divide it by 3. Time divided by 3 when we're working with the fact that it says the half-life of mercury is 3 days. So whenever you're dealing with these half-lives, you're going to take the time and divide it by 3. That's part of the formula for the half-life of a sample. So this looks like finding our function at 20, because we're looking at our sample after 20 days. So we have 50 and then 0.5, 20 divided by 3 as that exponent. And will you take a minute to go ahead and determine what is that going to be? How many grams will remain? There will still be a little bit here. It would be 0.49 grams of that mercury after 20 days have passed. So that is exponential growth and decay. But what is meant by this continuous growth or decay? What that means, ladies and gentlemen, is that sometimes a quantity is consistently increasing or decreasing at an exponential rate, and not just after a certain amount of time has passed, like a year, a month, a day, an hour, but it is continuously increasing or decreasing. And the formula that we use to find the amount or the balance is going to be A equals PE to the power RT, where R is positive for growth models and negative for decay models. So let's take a look here at problem 5. A garbage dumpster started with 4 pounds of garbage. The amount of garbage increased, so there's my keyword, increased continuously by 35% each day from this point forward. Find the amount of garbage in the dumpster after 2 weeks. So what does that look like? That looks like taking and using our formula, where it is our amount, P being the principal amount, the starting amount, which was 4 pounds. This is a base of E, and then our rate is 0.35, and our time that we're looking at is after 2 weeks, which is 14 days. So we want to go ahead and express that as 14. And so that gives us go ahead and figure out, use your calculator, what is that going to simplify to? You should have a whopping 537.16 pounds of garbage after those days have passed. And problem 6, the population of a town is declining at a continuous rate of 1.5%. All right, we saw that word declining. That's going to be an indicator of a decay model. If the current population is 16,000 people, find the population in 8 years. We will do so, because this is a continuous model, by starting with our initial amount, our principal amount of people, 16,000, base of E, that natural base, and it is a rate of 0.015, and our time that we're looking at here is years, and that is 8 years. So what is the amount going to be in this town after 8 years? There will be a total population of 14,190 people. All right. So to wrap it up here, I just want to show you all what logistic growth functions are. Sometimes we have a quantity that exponentially increases, but then levels out, and it approaches this horizontal asymptote like you see here. You see how it does like that? Sometimes it won't grow forever, but it ends up flattening out. And logistic functions look like this example here. The model of it looks like this. Where C, let me highlight that, C is going to be that asymptote, that horizontal asymptote. So we've got that C value, and the A is still that initial amount. E is that base, that natural base like we saw previously. And, oops, I'm so sorry. And R is going to be the rate, and X is whatever input we're dealing with, typically time. So here is what COVID actually looked like. This whole idea of wanting to flatten the curve, that's what they were talking about. So if a disease like COVID begins to spread in a town of 20,000 people, after T days, the number of people who have been infected by the disease is modeled by this function. Using the function, find the number of people infected after just 10 days. So that would mean that this function is growing, and we would want to see, let me rewrite it here, our function with a time or an input of 10. So that would be 20,000. And then 1 plus 1150E negative 0.95. And this is being multiplied by 10. So if we were able to flatten that curve and get the number of infectious rates not to continue escalating, but to instead flatten out, you would see that this is going to simplify to the number of people being infected is about, if we round to the nearest whole person, 18,415 people. All right. Now, what about this one here? The population P in millions of a country from 1850 to the year 2000 is modeled by the equation below, where T is the years since 1850. Using the function, find the population in the country in the year 1920. Well, we are trying to figure out what happens here. This population just doesn't keep going off the charts. It does eventually kind of taper off, which makes sense, right? Because a country can only really support so many people, and because of people moving and just, people coming to the end of their lives, it doesn't just keep going and going and going and growing and growing and growing. It does taper off. So we want to find in the year 1920. So what that means is we're going to have to look at, okay, a time between 1850 and 920. What time are we looking at? That's going to be a total of 70 years that have passed. So we're looking at what is the population where our input is 70 for this model. So that, ladies and gentlemen, needs to get just plugged into your calculator. And let's see, what is that population going to be? You should find pretty significant, this population in millions, not to be confused, it's not a population of 12.19, but it's 12.19 million. Make sure you've got the correct units there, otherwise that would be a little bit confusing. So there you have it, ladies and gentlemen. This is a look at modeling real-world situations and analyzing them using exponential growth and decay models. If you had any questions, would you please take some time to share those now? And until next time, stay fired up, y'all.